So today I'm going to be presenting over three-dimensional printing and artificial organs. So why is this important? Almost 120,000 people in the United States are on the transplant list currently. This list grows by one person every 10 minutes. Although there were only about 10,000 donors in 2017. So about 20 people die every day waiting for a new organ. This graph over here shows the percentages of people on the transplant list. Over 50% are still waiting for a donor organ. Almost 40% are deceased donor transplants, and the other 10% either were too sick to receive a transplant or died before they got an organ. So advances in technology the past few decades have seen a tremendous growth in the technology utilized to create artificial organs. One of those advantages has been the use of three-dimensional printers, and the reason that three-dimensional printing is becoming so popular now is because it's much more accessible to the general public and general consumer. Some of the past techniques used to create artificial organs have not been as precise or detailed in their creation as 3D printers can be. The creation of bioink and other major components for the 3D printer has allowed them to print whole organs that can survive on their own in the lab. Although this hasn't been tested with human subjects yet, hopefully we'll be able to test them in the future. How it works, three-dimensional printing. So no matter what you are printing or what 3D printer you are using or material, the printing process remains virtually the same. The first step is to create a blueprint of the object using computer-aided design software, otherwise known as CAD. Next, after the blueprint is created, the printer must be prepared, which could be from refilling the raw materials or preparing the build platform for the object to be printed. The printing material is liquefied as it comes out of the 3D printing nozzle, and once it is printed, it solidifies before the next layer is printed on top of it. The 3D design is split into 2D cross sections, which allow the printer to know exactly where it needs to print what. The entire process can take minutes to days, depending how complex the object you are printing is. And after printing is completed, every object requires post-processing, which could be from unsticking the object from the build platform, or removing the support structures, or brushing off excess powder that resulted from the printing process. There are quite a few different types of 3D printers, all which do different things, some of which include material jetting, powder bed fusion, and directed energy deposition. So biomaterials and bioink are what is used in the printer to print the objects. The main components of these bioinks are human cells, hydrogel, and a sugar matrix. Bioinks are based off of biopolymers that you would find in the human body, such as gelatin, collagen, fibrin, alginate, and many others. A key component to function properly for the organs are encapsulated cells that are able to survive under high stress that is caused during the printing process, and also are able to resist the hard cross-linking steps. So cross-linking is a technique that they use to further stabilize the bioprinted structures. There are two types of cross-linking, one of which is the physical cross-linking, which is accomplished through non-covalent or ionic interactions. The other is chemical cross-linking, which is done through the formation of new covalent bonds, and that makes it more stable than the physical cross-linking over time, which is important for organs because they need to be sustainable for extended periods of time. Keratin-based hydrogel is a new type of bioink that they have created. Some of the benefits of this are the low cost because it is derived naturally from human hair cortex, and it is physiologically biodegradable and can self-assemble or be cross-linked to form hydrogels used in bioink. Keratin fibers, microporous scaffolds, and sheets have been used in applications such as bones, muscles, skin, and nerve regeneration. Keratin contains elements that support cellular attachment and the binding of proteins. This keratin-based hydrogel can be used by formulating a photo cross-linkable resin and using it in a UV lithography-based 3D printer. This picture shows the different types of ways keratin can be used, one of which is wound dressing or hemostat, and it shows you the different types of mediums keratin can be made into. For printing organs, since 3D printing processes are usually the same, printing organs follows the same basic steps as other printing processes. The first step is to create a computer-aided design model of the tissues that are being printed for the organ. The 3D model is then again split into 2D horizontal slices to provide the printer with more detailed instructions and to know what layer goes with what and what is in what layer. Next, the biomaterials must be processed and refined to be made into bioink hydrogel. For the last step is post-processing, in which printing organs differs from other objects printed three-dimensionally, in which experimenters must place these organs or tissues in a medium that allows them to mature and will allow them to function as a regular organ might. For printing heart tissues and valves, it is a very complex process and includes multiple different printing techniques and biomaterials to resemble what a real heart would look like. The heart has three main types of cells that make it up, which are the cardiomyocytes, cardiac fibroblast, and endothelial cells. Three main types of tissues that are also found in the heart are myocardium, endocardium, and pericardium. Since they have various cells and tissues in the heart, it requires different printing processes and material to make those. The implications for the study are that three-dimensional printing can be used for a variety of different organs and tissues such as vascular, heart, liver, cartilage, bladder, and skin. If they continue to improve the biomaterials and bioink to make these artificial organs, eventually they could be used in humans, and transplant patients would not have to wait to find the perfect organ donor match. This technology could save hundreds of lives each year and would make the transplant list a thing of the past. 3D printing can potentially change the future of tissue engineering, and from fabrication of organs and tissues to pharmacological investigations for diseases to find out what exactly is wrong with a patient and how they can fix it. And then these are my references.